This reaction is called a transesterification. So in this process, we're going to be switching this ethyl ester for a methyl ester. Now, one of the things that's important to consider in this reaction as we run it in a lab is that in order for this reaction to happen with a high yield, we're going to have to use an excess of the alcohol that we want to be present in our product. So Le Chatelier's principle in that case will then favor the formation of the ester that we would like from the original ester. So under the conditions of this reaction, our ester is going to protonate in the initial step of the mechanism. But we have two oxygens in our ester. So we can use the resonance structures of this ester in order to understand which oxygen is going to be the one that protonates. As we know with all carbonyl compounds, we have a significant resonance structure that pulls those electrons up to the oxygen to separate that charge in that carbonyl bond. That separation of charge looks like this. Whenever you get stuck in a mechanism, you can use resonance to help you determine where the electron density in your structure is. So that in this structure, as we look at it, we see that we have a significant electron density at the oxygen right here that was originally a part of the carbonyl. Now, if you're wondering about this oxygen, can this oxygen protonate? Will this oxygen protonate? And to answer that, we can look at one additional resonance structure that shows that the lone pairs on that oxygen are actually being pulled toward that carbon in an additional resonance structure. That means that that oxygen really doesn't have the electron density in order to be able to pick up that proton from the acid in the reaction. The oxygen of our carbonyl has much greater electron density and therefore is going to be the much more basic oxygen of our ester under the conditions of this reaction. So what this series of structures shows us is that it's this oxygen right here that has the greatest electron density. Okay, that means that that's the oxygen that's going to pick up the proton under the conditions of the reaction. So if we get back to the mechanism, we have our ester under acidic conditions, and so this ester is floating around in a reaction that has a lot of acid. H3O plus is just a generic acid for us, so this could be a number of different specific compounds. And so the lone pair on this oxygen is going to pick up that proton, give the electrons back to the oxygen in the molecule of water, and that's going to give us our activated ester. So that gives us our activated ester, which remember is a much better electrophile than the ester before it picked up that proton under acidic conditions. So now our nucleophile can attack this carbon of the carbonyl, where we could show it from this structure, or we could also show the resonance that pulls those electrons up to the oxygen. Either way to show that step is fine. So in this case, our nucleophile has to be the methanol. And remember, the conditions of this reaction tell us that we're going to use a large excess of this alcohol because we want this to outcompete any other possible nucleophiles that we have in our reaction. So the methanol attacks, and we get a tetrahedral intermediate. This is the tetrahedral intermediate that we have. Now remember, this is a stressed intermediate because carbon is bonded to 3 electronegative oxygens. And so one of these groups is going to fall off as a leaving group. And right now, if this tetrahedral intermediate were to collapse, the best leaving group is going to be this molecule of methanol, which sends us right back to the beginning of this reaction. So in order to keep this molecule of methanol there, we need to have a base, like a molecule of water, remove that proton, give the electrons to that oxygen, and give us this new neutral tetrahedral intermediate. Now, this tetrahedral intermediate is not going to be very good at collapsing, because if this tetrahedral intermediate collapsed, it would have to kick out hydroxide, or ethoxide, or methoxide. And none of those are good leaving groups under the conditions of the reaction, which you'll recall are acidic. And so in order for this tetrahedral intermediate to collapse, we have to have one of these oxygens pick up a proton. The proton is going to be picked up from the acid in our solution, and I have an oxygen here with 2 lone pairs, an oxygen there with 2 lone pairs, and an oxygen there with 2 lone pairs. And all of these oxygens are just about equally as likely to pick up that proton compared to any of the other oxygens that we have in our reaction. But the only oxygen that picks up that proton and moves us forward in the reaction is going to be when the oxygen of the ethoxy group picks up that proton. That now gives me an intermediate that looks like this. So from this structure, if this tetrahedral intermediate were to collapse, the leaving groups that I have as a possibility are hydroxide, methoxide, or ethanol. And so the best of the leaving groups is going to be this neutral molecule of ethanol. So now I can use the lone pairs on this oxygen to help kick out that molecule of methanol, or the oxygen can simply take its electrons and leave, and either way you show that mechanism is fine. So if the molecule of ethanol just takes its electrons and leaves, similar to what we would have seen with our ether mechanisms way back in the beginning of the semester, the product that I get of that step looks like this. I also lost my molecule of ethanol during that process as well. And these are reversible steps in my reaction. Okay, all of the steps throughout this mechanism are reversible. This carbocation is a resonance stabilized carbocation. We have 2 oxygens with 2 lone pairs on either side. So both of those oxygens can help stabilize. But if I use the alcohol to help stabilize, I get something that starts to look very close to my product. Which is that structure there. So the last thing I need to do in this reaction is have a base like a molecule of water, potentially this molecule of ethanol right here, come along and remove that proton. And that's going to give me my final product out of this reaction, which is that methyl ester. These final steps here are also reversible. This step right here we drew is actually a resonance step. So it's not equilibrium arrows in your reaction. It's actually going to be resonance arrows between those 2 structures. But again, what's going to drive this reaction forward, what's going to help us make the product that we want to make out of this reaction, is the fact that we're going to run this reaction with a large excess of methanol, which is the alcohol that we need to be in my final product. So overall, this is the transesterification mechanism for the ethyl ester to the methyl ester.